Okay, introduction to statistics. Let's get started. Okay, what is statistics? Why do we do it? Statistics is the science of studying and drawing conclusions about data. Okay, why is it going to be important for us in this program? In this program, we will be analyzing data. We're especially looking at evaluating the impact of development programs. One of the biggest focuses of this program is to evaluate development programs. When we evaluate development programs, what it is that we're doing is we're collecting data. Data on individuals who have received some development program. We're collecting data from them, and we're analyzing that data to determine whether or not a development program has had an impact, and if it has had an impact, how big that impact is, whether it's positive or negative. Okay, so we use data to do that analysis. All right? Statistics is kind of the mathematical foundation of that analysis. So that's what we want to do. We want to lay that foundation so that when we go into classes like econometrics, we're able to handle data, use data, understand data, and analyze it to drive the conclusions that we're looking for. Does that make sense? Okay, so that's the basic reason or motivator for why we're doing this. Okay? And so I want to begin by just doing some basic concepts, and then we're going to go through a bunch of sections, and we'll have some practices on the in the workbook. Okay. Now the first thing that I want to look at, we're just laying the foundation. The first concept that I want to illustrate is the concept of a population versus a sample. Okay. When I refer to a population in statistics, what I'm referring to is the collection of all of the individuals within a particular population that I'm interested in studying. I might be interested in studying the entire world population, all human people. That includes, that's the population of all the people in the world. I might be interested in studying the impact of a development program in northern Ghana. And so my population is all the individuals that live in northern Ghana. I might be looking at a research project that's studying the impact of internet learning on students at Catholic University of America. And in that case, my population would be all the students at Catholic University of America. The population is the target group of people for which I'm interested in studying. I'm interested in studying that group of people. I'm interested in knowing the impact of some program on that group of people. That's my population. Whatever my development program, whatever impact that program might have on the population, that's the thing I want to find. I want to find how this program will affect that population of people. I want to know that if we introduce internet learning at Catholic University of America, how will that affect grades of any student? How does that affect the grades of students at Catholic University of America? I want to know things about that population. I want to know things about the individuals that live in northern Ghana. If I provide fertilizer subsidies, how does that affect farmers in northern Ghana? Really, what I want to know is the impact on the entire population. I want to know the impact on every single individual in a population. The problem is that we almost never have the resources available to collect data on every single individual within a population. Does that make sense? If I want to know the impact of internet learning on students at Catholic University of America, if I wanted to know the impact on every single individual, I would have to have data. I would have to collect a survey on every individual. That might be possible. If I wanted to know the impact of a fertilizer subsidy on farmers in northern Ghana, that would be a lot of data. That would be a lot of people to interview, to collect data on the entire population. If I wanted to know the impact of something on on humans in general, it would be really hard to collect data on every person in the world. Okay? So what we do in statistics is we collect data on a subgroup of people, our sample population. We collect data on some smaller group of people. And we look at that data, and then we make inferences. We make estimates about the impact of something on the larger population, but just looking at the sample. So if I want to know what's the impact of a fertilizer subsidy on farmers in northern Ghana, I'm not going to collect data on every single farmer in northern Ghana. I'm going to collect data on a subset and then use statistics to be able to infer the impact on the whole population from just the data that I collect. Any questions on that so far? So we have our population. So anytime I say if I say the population average, that means it's the average for the whole population. If I say the sample average, that's the average of the sample. Okay? The population is everyone. That's the reality. We want to know what happens to the whole population, but we never know that directly. We only know what happens to the people in our sample. So we use the sample to make estimates about what would happen for the whole population. Okay? So my example is, well, what if the whole population is the students at Catholic University of America, but I use as my sample the students in our program, the Integral Economic Development Master's Program. So that would be an example. It's a subgroup, a smaller sample, a collection of individuals from the whole population, a collection of the individuals from the target population, and we'll study them. And then we can estimate what would happen with the full population. Is that clear? All right, so that's the first topic. We're going to be a little bit sporadic here. We're just going to introduce some concepts, and then we're going to become a little bit more structured in just a second. The next thing I want to do is I want to talk about notation that we're going to use and begin to explain a couple of concepts. Throughout this lecture, we're going to use some notations very common in math and very common in statistics. The first one is the sum. The sum notation. It's this capital Greek letter sigma. That means the sum. It's the sum of a number of different elements in the data set. I'll illustrate that in just a second. X represents a variable that is made up of many individual data values. I'll demonstrate this in just a moment as well. N is the number of the data values in a sample. Remember I said there's a population and then there's the sample? Lowercase n always refers to the number of people in your sample. Capital N always refers to the number of people in the population. So if we're looking at a study of farmers in northern Ghana, capital N might be 2 million. And then, but I only collect data on 2,000. So lowercase n is 2,000. See what I mean there? Okay. Let's take this. Let's make this clear. Let's talk about the sum operator. All right. We're going to use this a lot, so I just want you to be comfortable. When you see that capital sigma, you know what that means, and you know what's about to happen. All right. So the sum symbol, what that means is that we're adding up elements in a variable. So here's an example. Xi, okay, that lowercase I is an index. It can take different values. There's x1, there's x2, there's x3. So I can take different values. In this case, it can take a value from 1 to 3. So that means x could be x1, x2, and x3 in this example here. The sum is that means that I'm adding up x1 plus x2 plus x3. Okay. So I want to practice this by looking at this little mini data set here. Here's a mini data set. I represents individuals, so individual 1, 2, 3, 4, 5. And then xi represents some variable. You know, x might be, maybe x is your hourly wage. Okay? So person 1 is earning $10 an hour, person 2 is earning $4 an hour, person 3 is earning $6 an hour, person 4 is earning $8 an hour, person 5 is earning $12 an hour. Okay? I want to know the sum. What's the sum of this variable xi? Can you do that for me real quick? What's the sum of xi? And actually, I'm noticing a typo here. This is the sum from I to 5. All right, so we're summing up all these values. What is the sum?
40.
So we got one vote for 40. Any other votes? Anyone else think it's different? Do you have any dissenting opinions? 40? All right, we have no dissenting opinions. How did you do it?
I differ.
It's just 10 plus 4 plus 6 plus 8 plus 12. Okay, straightforward. So everyone's comfortable with this. Every time you see that capital sigma, you know what to do. Right? Okay, great. Excellent. All right, so now I want to go in deeper with some of the other issues we were talking about. Introduction to random variables. A random variable it's a mathematical expression that can take different numerical values from a predetermined set of possible values. Okay? So a random variable, this is like in the first slide we had xi. So we can say that there's some random variable x. X can take different values. It could be 1, it could be 10, it could be 5, it could be any number of values, okay? So x is mathematical notation, it's a mathematical expression for something that can take multiple different values. Whenever we're working with data, we work with variables. Just like our little mock data set here, xi, or x, is a variable. It can take different values depending on what individual or what observation it's referring to. Alright, so x is a variable. The point is that x can take on different values. And the values that it can take come from some predetermined set of possible values. Sometimes you can have a variable, let's say I have a variable x, and it can equal only 1 or 0. We would call this a binary variable. It can take the values of 1 or it can take the value of 0. We also might have a variable called a continuous variable. A continuous variable can take any number between some minimum and some maximum. So I could say x is a variable that could take any value between 0 and 1. So then x is a variable that could be 0, it could be 1, and it could be any number in between. It could be 0.9999999 off to infinity. It could be any number between 0 and 1. Okay? So a variable is a mathematical expression that can take different values out of some predetermined set of values. Okay? We typically will write variables. We might write them as a capital letter or a lowercase letter, but then individual elements, individual values are usually indexed by something. So if I have a variable x, an individual observation might be xi. So I have a variable x, and then it can take x1, x2, x3. These are all unique values of the variable x. Any questions on that so far? Okay. So, a random variable is a mathematical expression that can take different values from some predetermined set of values. Now the probability that a random variable will take any particular value is given to us by a probability distribution. The probability distribution is a function that determines the probability that the variable will actually take any particular value. Okay, so let's go a little bit more deep on this. So a random variable, like I said, we're going to use the example of y. Y is a random variable. Well, yi is a particular value of y. So I have some random variable y, So here's some small mock data set here. I have some variable y, and then lowercase I to indicate different observations or different individuals. We have observation 1, and then the unique value of y for observation 1. So that's lowercase y1. And then we have y2 and y3. These are all unique values of the variable y. Our first little data set did a nice job of illustrating this. Let's imagine I have a data set on 5 individuals and I have their wages, how much money they make per hour. Person 1 makes $10 an hour. Person 2 makes $4 an hour. Person 3 makes $6 an hour. Person 4 makes $8 an hour. The wages, x, that's a variable. It can take different values. Right? It's a continuous variable. It can take any value from 0 potentially to infinity. Okay. Now there's some probability that any particular value is going to be observed. So P of yi is the probability that yi will occur. What's the probability that if I just draw an individual at random, I just go out and I just ask some random person what their wage is, what's the probability that they'll say $10 an hour, or $5 an hour, or $20 an hour? There's some probability that that observation will be the observation that you get if you go and you just ask someone randomly. So we have a random variable that has different observations, and then there's some probability of observing that individual observation. Okay? A probability density function. A probability density function is a function that gives you the probability of seeing that particular observation. So let's look at an example of a discrete random variable, and then we'll look at a continuous random variable in a moment. Okay, a discrete random variable can take discrete values. The classic example is a random variable that can take either 1 or 0. That's what's called a binary variable. A binary discrete random variable. So let's just think of an example. Here's an example where I have a binary variable, can be either 1 or 0. And there's a 75% chance that my random variable will be 1. And there's a 25% chance that my random variable will be 0. Another example would be, imagine that I have a coin. So I have a coin that's heads and there's tails. Okay? I can generate data from this coin. Let me do it on the board. So I have observation I, and then I have the outcome of my coin flip. Okay? I'm just going to call it X. Okay? X is the outcome from my coin flip. So we're going to collect some data. I'm going to flip the coin 5 times. Alright? So I'm going to get 5 observations. Alright, I'm going to flip it. Let's see what happens. Tails. Let's say tails is 0. Alright? Every time I get a tails, I'm saying that that's a 0. Okay? Heads is going to be 1. Alright, so I got tails. Heads. That's 1. Dropped it. It's heads. I'm collecting data right now. Heads. Heads. Alright, so we just collected data on coin flips. This is a random variable. It shows you whether you got heads or tails. It's a discrete random variable. It can only take 2 values. It's either heads, 1, or tails, 0. What's the probability that I will get heads?
Half.
Half. It's 50%. Right? A 50% chance of getting heads and a 50% chance of getting tails. Coin is one of the best examples of something that will generate a random variable. It helps us illustrate what a random variable is. A random variable is some mathematical expression that can take different values. This will generate a discrete random variable. It takes zeros or ones. There's a 50% chance of getting heads. There's a 50% chance of getting tails. What I have here is the graph of a probability density function. It's not for a coin, because for this one, there's a 75% chance of getting 1 and a 25% chance of getting 0. But this graph shows me the probability of the different values. So here I have y equals 1, and then it shows me that there's a 75% chance of getting y equals 1. And I have y equals 0, and it says it's a 25% chance of getting y equals 0. So this is a graph that demonstrates the probability of getting the different values. Does that make sense? It's a probability density function. It shows the probability of getting the different values. We can think of another example of a random variable. Let's see. There are 3 faculty members on the Integral Economic Development Master's Program faculty team. There's myself, Dr. Aguirre, and Dr. Cruz. 3 full-time CUA faculty members. Okay? So we have 3 people. Now, what is, let's say that I had a random variable, and that random variable was gender. So it's the gender of the faculty member. And you, with your eyes closed, you just picked one of the faculty members. What's the probability that you'll pick a male faculty member? What's the probability that that random variable will be male? If you just picked one of the faculty members at random, you didn't know who you were picking, just picking one at random, what's the probability that that faculty member will be male? There's 3 possibilities. There's 3 possible faculty members. How many of those faculty members are male?
1.
There's 1. So it will be 1/3. There's a 1/3 probability. 1/3 probability that that faculty member that you draw will be male. So the probability density function would show a 2/3% chance of picking female and a 1/3% chance of getting male. Does that make sense? You see how maybe the gender is a random variable. You go and you take a sample. You go and you pick randomly a faculty member. There's a 1/3% chance of getting male, 2/3% chance of getting female. Okay. Any questions so far?
Okay.
It's okay? Okay. Now let's think about a continuous variable. So far this has been discrete. One, either heads or tails, male or female. Alright, now we can think of a continuous random variable. This is something that can take any value. This is like the wages. You can get paid $0 an hour. You can potentially get paid infinity dollars an hour. Although realistically there's some maximum. I mean there's some amount that the highest paid person makes. But it's a pretty big spread. There's a lot of options. So we call it continuous. It can take any value between 0 and the maximum. Alright, that would be an example of a continuous variable. The probability density function for a continuous variable does, for the most part, the same thing that the probability density function does for a discrete variable. And that is, it communicates to you the probability of any particular value being drawn, if you will. If I go out in the general population and I just pick somebody randomly and ask them what their wages are, the probability density function for that population will tell me the probability of picking someone with that income. Does that make sense? Okay. So probability density function is graphed like this. There's lots of different kinds of functions because there could be all kinds of different distributions of income. Imagine that we go into a city where almost everybody makes $1 an hour, and then one person makes, $1,000 an hour. Huge inequality. That distribution would be weighted heavily towards the person that does the people. There's a lot of people. It's a very high probability of picking someone that makes $1 an hour, and a very low probability of picking someone that makes $1,000 an hour. All right. Or we can have a distribution that's a little bit more even. A distribution where there's a couple of people that make $1,000 an hour, and there's a couple of people that make $1, but most of the people are in the middle and make somewhere around $10 an hour, $20 an hour. And so if you were to go into that population and pick someone randomly, it's most likely most of the people are going to be right there in the middle. That's a distribution that looks like this. This is the probability density function for what's called a normal distribution. A normal distribution gives us, it basically presents to us the probability of drawing some value from a population. All right, so this is a standard normal distribution. This gives us the probability. And so when the probability is really high, so when the function is really large, when the probability is high, that means it's much, much more likely to draw that corresponding number. The standard normal distribution is centered around 0. So it means it's really likely to pick 0. There's a lot of people that have 0. There's very few people that have 4, so the probability of picking 4 is very low. There's very few people that have -4, so the probability of picking -4 is really low. Do you see how the curvature of this function kind of can communicate to you the probability of the different numbers? Does that make sense? Okay. Now, probability density functions for continuous functions, they're a little bit tricky. When you look at this, I might want you to think that this communicates to you the exact probability of each value. But really the way that it works, and I don't expect you to know the math here, but the way that it really works is that the probability density function will communicate to you the probability of picking a particular value within a certain range. So if I said, what's the probability of me picking a number between -0.2 and then 0.2, the way that I would determine that probability is by taking the integral under the probability density function between -0.2 and 0.2. We don't have to go into all the, we're not necessarily going to go into that level of detail, but I just want to communicate that so that it's understandable. Generally speaking, the probability density function communicates to you the probability of realizing particular outcomes. Does that make sense? Okay. With that said, I want to do our first practice to give us some idea of how random variables work and some idea of the probability density function. Okay, so let's look at your first activity. All right, what I have here is a bag, and in this bag there are 10 wooden balls. Okay, and on each of these balls there's written a number. All right. And what you're going to do is you're going to reach your hand into the bag and you're going to pick 4 balls. Well, there were 10, now there's 9. All right. You're going to pick 4 balls, okay? Then you're going to write down the numbers on your worksheet. All right? I want to communicate what it is that we're doing here. We are saying that this bag contains the full population. All right? Just imagine that we're doing a research study on a population of 10 people. You're not going to be able to collect all 10 data points. You're only going to be able to collect a sample, 4. All right? So you're going to reach your hand in the bag and you're going to collect your sample of 4 observations from the population. Okay? And then you're going to write them down in your table. This is going to help just illustrate what a random variable looks like and what we talk about when we talk about collecting data from a population. It's a total population here of 10. Okay? You're going to collect your sample. All right. So
We're
let's
not
do
going
it.
to do it with replacement.
No, it's not with replacement. You pull it out, you write it down, and then you pull another one. You don't put it back. You'll put them back in after you're done drawing 4. So go ahead and draw 4. So what we're doing right now, let's imagine, let's give an example of this. So let's say we're studying farmers in northern Ghana. Okay? And so we want to look at their income. We want to look at income. We're collecting income data on farmers in northern Ghana. All right? And just for our example, let's say that there's 10 farmers total. In all of northern Ghana, there's 10 farmers. But we can't afford to go and collect data from all 10. It's too many. So we're only going to collect data from 4. All right? So this is what we're doing. We are collecting income data on northern farmers from Ghana. Now, if we wanted to get a representative sample, a sample that gives us a good indication of what that population is like, we do it randomly. And that's what you're doing right now, is you're collecting random data. You're just picking individuals randomly from this population. All right? This is income data. We're calling it Y on there, but it's income data. Okay? So income is a random variable. It could take any number of values. And every time that you go and you survey someone, you're observing a particular value of that random variable. And so that's what you're doing right now. That's it. And we're going to use this in some of the later activities as well. Okay, while you're picking that, I'm going to erase. So the first part of that activity there is just to illustrate what a random variable is. How income can take different values. But then I also want us to draw a graph of a probability distribution, probability density function, just so we get a good idea of what that is. Okay? How are you guys doing so far? This review? Comfortable with random variables? PDFs? Yeah? What's that? Very much. Very much so. Okay, good. So I could actually speed up. Yeah? Okay. That's good to hear. Okay. Well, let's just finish this activity for completeness sake. Alright. So now I want to get an understanding of the total population. So we're going to figure out what the population is, and then we're going to look at the probability of drawing any particular value. Okay. There is one value of 100. There is one value of 600. There's one value of 700. One value of 800. There's two values of 900. There's one value of 1,000. One value of 1,100. 1,200. And then 1,700. So then what's the probability density function look like? Can you draw the graph on your paper? go ahead and draw it. I've made this just to prepare us for it. Question?
Yeah, that looks good. I wouldn't connect the lines because there's no values between. It would just be horizontal, it would just be vertical bars. But other than that, you have the right idea. It would just be like, you could do a thick bar or a skinny bar. It would just be vertical. It would just be vertical here. You wouldn't connect the line. You wouldn't connect the dots. But other than that, you have it right. I'll do it on the board in just a minute. Yeah.
Okay, so let me just show you what I'm looking for. So probability density function is just going to give you the probability of the different values. This is a discrete random variable. It takes only 10 particular values in this case. Now, if we had a larger population, we would ultimately consider this to be a continuous variable, but we don't need to think about that now. I just want to give us an idea of what this means. In this example, we have one value for all of these and 2 for this. There's 10 total. So that means there's a 10% chance of getting this, a 10% chance of getting that, a 10% this, all these are 10%, 900 there's a 20% chance. So there's a 10% chance for 100, wow, I missed that a little bit here. Right, there's a 10% chance for 100, 10% chance for 600, 10% chance for 700, 10% chance for 800, 20% chance for 900, and then 10, 10, 10, and 10. So this gives us our probability distribution. This tells us what's the probability of getting the different values. And we did this just to illustrate this concept, what a probability distribution is. Is that clear for everyone? Okay. Good. Well then let's move on to the next example, or the next topic. Now that we have an idea of what a random variable is and what a distribution is, let's look at some descriptive statistics. One of the things that we're going to do when we analyze data, the first thing that we do, right, we collect data. That means we're collecting variables. Variables have all these different values, so we're going to have a data set with different observations of variables that have different values, okay? So we're going to have a data set. And then one of the first things that we want to do is just get some descriptive statistics. We just want to have an idea of what's our data look like? What's the distribution look like? All right? So then the first topic I want to look at is descriptive statistics, just some basic statistics to get some idea of what our data looks like, what our variables look like. So let's do that. First, let's look at a measure of center. By a measure of center, what I mean is, what are the variables that are most likely in the data set, or that show up the most in the data set? There's several measurements of center, but the one that we're going to look at exclusively here today is the average, or the mean. All right, so then let's look at the mean. Now, in a data set, there's a population mean and there's a sample mean. The mean is, like I said, it's the average. It's you add up all the values in the data set and you divide it by the number of values. So there's a population mean and a sample mean. Okay? Let's look at that. The population mean is if somehow you had data on every member of the population, you could add up their values. So let's say we're looking at the random variable income. You can add up all the incomes from all the individuals in that population, and then divide by the number of people in that population, and that would give you the population mean. Okay? But like I said before, actually let me point this out. So what do we have here? Mu, the Greek letter mu, we usually use that to represent the mean. And the mean is the sum of all the individual values of the random variable divided by n, the number of members in that population. Right? So this notation should be comfortable now that we've reviewed the summation notation. But we normally don't have the population. We don't have data on every member. You don't have data on your paper. You don't have data on the population. You have data on a sample, right? A sample mean, the same formula. It's you add up all the individuals in your data set, and you divide it by the number of individuals in your data set. And we usually represent the average notationally. We'll represent that as x, if that's your variable, x, with a bar over top. So x bar. That'll be the average, the sample mean. Okay. So that gives us an idea of what is the average value in our data set. That can be useful. Let's say we collect income data, and we just want to have an idea of our population. We've collected all this income data from northern Ghana, and we want to know, what's the average income level of farmers in the area. That doesn't communicate to us all the information that we want to know about the farmers, but it gives us some idea. And we're talking about a population of very wealthy farmers, or we're talking about a population of very, relatively low-income farmers. The mean gives us a measurement of kind of the middle of the data. Okay? But we want to know more about the data than just the mean. We also want to know how is the data dispersed. We can imagine a scenario like this, for example, where the data has a lot of dispersion. There's a big range. It goes from 100 all the way up to 1700. There's a big range in the data set, in our data set here, in our population data set. There's a big range. There's a lot of variation in this data set. So we also want to know some measurements of variation. All right? So this is just kind of an example. The extent to which individual pieces of data differ from another. So here's an example of M&Ms, the candy. There's no variation here. There's no variation. All the individual members are the same as one another. The average color is green, and they're all green. No variation. Right? Here's an example of some variation. We have a bunch of different colors. Right? So that's just an example of variation. Okay. So here's a question for you. Of these two distributions, right, these are probability density functions. They give us distributions of data. Which one of these two has greater variation? Can I see a raise of hand for anyone that might have the answer? Which one of these has greater variation? Distribution 1? We have one vote for distribution 1. Anyone else? Any other ideas? Talk me through it. What's variation mean? What's variation mean? Variation means that there's differences among the different individuals. So if there's more variation in the data, then there's a greater probability of getting variables that are farther away from each other. And the data isn't all kind of pooled in the middle or for any particular value. Probability density function gives me the probability of the different possible values. So if there's a lot of probability for one particular value, a lot of probability for one value, very little probability for any other values, then that would be a data set that doesn't have very much variation. But if there's a data set that has a lot of probability for a lot of values. There isn't one value that dominates, that hugely dominates all the rest. But there's a lot of variation for a lot of variables, or a lot of values. What would those distributions look like? Maybe I can use some examples. Let's think back to our example from northern Ghana. Okay, we're thinking of farmers from northern Ghana. Let's hold that in our minds. Let's say we have, let's say there's 1 million farmers that we're thinking about. Okay, and we're just using this as an illustration. Okay. Let's imagine a scenario in which there's very little variation. 90% of the farmers all earn 10,000 Ghana cedis a year. 90%. There's like one person that makes 20,000 Ghana cedis a year. There's like one person that makes 1,000 Ghana cedis a year. There's 90% probability of being right smack dab in the middle at 10,000 Ghana cedis a year. What distribution would that look like?
Second.
The second distribution. Okay. Here's an example. Like, obviously my numbers aren't calibrated. The illustration doesn't match these numbers, but bear with me here. So we're imagining that right here in the middle is 10,000 Ghana cedis, and lots of people. There's a very high probability of observing someone with 10,000 Ghana cedis. Very low probability of seeing someone out here, 20,000 Ghana cedis, or 1,000 Ghana cedis. All right. So you go out there, you ask the farmers, there's no variation. Every farmer you go to, 10,000 Ghana cedis, 10,000 Ghana cedis, 9,500 Ghana cedis, 10,500 Ghana cedis. Everywhere you go, everyone you talk to has the same amount, pretty much. Very little variation. So you're going to see a lot of probability right here in the middle, and very little probability out here on the edges. That makes sense? Now, alternate example. You go out, and they are all over the place. You go into a village, you talk to one farmer, 10,000 Ghana cedis. You talk to another farmer, 20,000 Ghana cedis. You talk to another farmer, 3,000 Ghana cedis. You talk to another farmer, 7,000 Ghana cedis. You talk to another farmer, 8,000 Ghana cedis. As you go through, you talk to all these farmers, and the data could be over here, the data could be over here. And so they're not all pooled around one number. In the example I just used before, I said there was a 90% chance of getting 10,000 Ghana cedis. But now in this new example, there's 40% chance of getting 10,000 Ghana cedis. And there's a 20% chance of getting 7,000 Ghana cedis. And there's a 20% chance of getting 13,000 Ghana cedis. You see what I'm saying? In this second example, you go out and there's lots of variation. What distribution would that look like? 1? So we're saying right here in the middle is 10,000 Ghana cedis, but less people have 10,000 compared to over here. More people are going to be out here. More people have 13,000. More people have 7,000. Do you see what I'm saying? So this one has more variation. So you were right. Boom. Does that make sense? Does this example help to make this concept clear? And does it help to make sense of what these graphs are? Because these graphs are important. We've got to have an understanding of what these graphs indicate to us. When I say the probability density, that is how much probability there is for a particular value. Okay. Any questions on that? Can you tell me what a probability density function is? Just conceptually. Can you tell me back what a probability density function is? Even just conceptually. And it's okay. And I just kind of want to have this conceptual understanding. It's a function that gives us the probability of particular values. That's not perfectly accurate. It's a function that will tell me the probability of a value lying between a certain range. But when we look at this graph, okay, I just want to have a conceptual understanding of what this graph looks like, a conceptual understanding of what a distribution is. This graph communicates to me the probability of observing particular values within my data set. So probability density function communicates to me the probability of observing particular values in my data. Does that make sense in terms of conceptual understanding? What do you think? Can you, just conceptually, what is a probability density function?
The probability density function shows the degree of occurrence
Okay.
of a particular event in a sample.
Excellent. Yeah. Okay. Good. Okay. How do we feel about that? Ready to move on? Okay. So that's variation. Now I want to get a measurement of variation. I want to get something that communicates that to me. So we said before we had the mean. The mean tells us the middle, right? I was just talking about that. Okay. In my first example, the mean is 10,000 Ghana cedis. In my second example, the mean is still 10,000 Ghana cedis, but there's a lot more variation. Right? So I want to know the mean. That gives me an idea of my population. But I also want to know the variation. I want to know how widely dispersed the data is. All right? So let's get some measurements of that. The first measurement of variation that I want to look at is range. That just gives us the range of possible values that you can have in your data set. What's the range of our data set? What's the range in our population? Here's all the values in our population. What's the range?
1600.
1600. How'd you get that?
Maximum minus the minimum.
Maximum minus the minimum. Okay, great. Does that make sense? That's just the range of the possible variables. That gives me some idea of the variation. Right? Tells me how low it can be, it tells me how big it can be. Oftentimes when you're reading papers or when you are writing a paper, you will report the minimum value and the maximum value of a variable. Okay, that's common. That still doesn't tell me much. Think of my two examples of my two farming populations. The first population, 90% of the people had 10,000 Ghana cedis. But it's possible that the range could have been the same. The lowest person in that data set could have had 1,000 and the highest person could have had 20,000. And the same thing with the second data. The mean could have been 10,000, with the lowest being 1,000, the highest being 20,000. It still doesn't tell me how much, what the dispersion of the data is like. It doesn't tell me which of these graphs I'm in. Yeah? Okay, so then let's go to another one. All right, so that's range, we just did that. Okay, variance. Variance is a measure of how dispersed the data is. All right? So variance is a measure of the variability that represents the mean of the squared distance of each individual data point from the mean of all the data points. It measures how much variation there is in a particular variable. All right, how do we calculate it? Again, we're going to have a population variance and a sample variance. If we used our data up here, we could calculate our population variance. On the paper that you have, you wrote down your values, right? You wrote down your observations. You collected a sample, so you can only do a sample variance. All right, I'm going to have you do it in a second. All right, but let's look at it. How do we calculate it? The population variance, we use the Greek letter sigma, sigma squared, that's our population variance. And the way that it works is we sum up the differences between each individual value and then the mean of the data. We sum that up. We take the individual value minus the mean, we square that, the individual value minus the mean, we square that, and then we sum that up. And then we divide by the number of members in the population. That is the population variance. We could do that here if we wanted as an exercise. We could calculate the mean. That is, we sum up all of these values and divide by 10. And then if we wanted the variance, we would take each member, 1,000 or 100 minus the mean, squared, divided, plus 600 minus the mean, squared, plus 700 minus the mean, squared, and so on. Sum those up. That'd be our variance. With our population, you do the same, with our sample variance, you would do the same calculation, except you use your sample mean instead of the population mean, because you don't know the population mean. And then you divide by n minus 1. We don't necessarily need to go into all the details as to why it's n minus 1 and not just n. Like you might ask yourself that question. But suffice it for now to say that basically what we're doing when we find the sample variance is we're trying to estimate the variance in the population. Remember what I said before, at the beginning of the lecture I was saying that what I really want to know is I want to know what the population is like, but I don't have all the data from the population. I only have the sample data. So everything that I do with the sample data is an attempt for me to estimate what's the reality in the population. So our sample mean is an estimate of the population mean. Our sample variance is an estimate of the population variance. And for reasons we don't need to discuss, if we divide by n minus 1, this is a better estimate of the sample variance. This is a better estimate of the population variance than if we just divided by lowercase m, just in case you were curious. Any questions on that? Okay. All right, so the steps to calculating the variance. I think you can see it in the equation, so I'll move. So we can just do an example, how to calculate the variance. Let's say we have some data set, x. X is our variable, okay? And these are the particular values of that variable, value 6, 10, and 15. Okay? The mean, what's the mean? Can anyone calculate the mean here real quickly? I'm going to count down. 5, 7? You think it's 7? Excellent. Okay, so we have the mean. All right. And now what we do is we take the difference between each value and the mean. There we go. The difference here is -1. Difference here is 3. The difference here is 8. All right. Then we square it. The square is 1. And the square of -1 is 1. The square of 3 is 9. The square of 8 is 64. Okay? And then we sum it, which actually, sorry, there we go. We sum it, that equals 74. And then the sum, this will give us our sample variance. Sum divided by n minus 1 is 37. Is that clear? Okay, now another measurement of the variation in a data set is the standard deviation. This is one of the most common that we'll see. The standard deviation is a measure of the variation of the values around the mean. It's the square root of the variance. So we just take the square root of the variance. So here's an example of our distribution we were looking at earlier. We've got some numbers superimposed on it. We just want to demonstrate what a standard deviation is. So this represents that normal distribution we were talking about before. And this demonstrates to us what a standard deviation looks like. A standard deviation gives us a certain amount of distance between the mean and then that particular data, and the particular data that we might observe within a distribution. All right, it's a standardized deviation from the mean. That's why we call it a standard deviation. So one standard deviation away from the mean, in either direction, on the horizontal axis, accounts for around 68% of the data. So we're looking at a normal distribution. 2 standard deviations away from the mean accounts for roughly 95% of the data, and 3 standard deviations represent 99% of the data. So standard deviations communicate to us some standard distance from the mean. So here's the mean. Here's 1 standard deviation larger than the mean. 2 standard deviations larger than the mean, 3 standard deviations larger than the mean. So the space between 1 standard deviation smaller than the mean and 1 standard deviation greater than the mean, that space is going to be around 68% of the data. How are we doing there? We don't need to know all, we don't need to fully get this, but this just gives us an idea of what a standard deviation gives us. Any pressing questions on this? Okay. How do we calculate it? We just take the square root of the variance. Straightforward. Okay. The unit of variance is the squared unit of the data. These can be very large, unwieldy numbers that don't make much sense. We like standard deviations because they're easier for us to understand. A variance, the unit is the squared unit of the data. So let's say the data is measured in dollars or gonocedes, like we were talking about income. The variance would be in units of gonocedes squared. That doesn't have a lot of meaning to us. So we'll typically use the standard deviation. The standard deviation, the units, would be in gonocedes. So if the average, okay, let's apply this to our example. This will help. We collect data from farmers in northern Ghana. The average farmer makes 10,000 gonocedes a year. Okay? That's the mean. The variation, the variance could be some ridiculously high number. Let's say it's just, it's 30 billion, and the units are gonocedes squared. The units of the mean is gonocedes, 10,000 gonocedes. That number makes sense to us, conceptually. I can think exactly what that is. Okay, 10,000 gonocedes. It's about about $2,000. Okay. But then when you say that the variance is 30 billion gonocedes squared, that doesn't make any sense. I can't think. That doesn't help me understand the variation. But if you take the square root, let's say that the standard deviation is 1,000, and then the units are gonocedes, 1,000 gonocedes. Oh, okay. That helps me just conceptually understand my data. If I have a mean of 10,000 gonocedes and a standard deviation of 1,000 gonocedes, that means that 68% of my data falls between 9,000 gonocedes and 11,000 gonocedes. 68% of my farmers have an income between 9,000 gonocedes and 11,000 gonocedes. That communicates to me a lot of information. That's very helpful. The variance is not very helpful. Standard deviation is really helpful. Does that make sense? Any questions on that? Okay. Okay. With that said, let's see. Let's do exercise 2 on your form.